I am indeed. Yeah.
Okay, we're gonna start the recording then. All right, so we're very happy to have Nima deliver the last lecture.
Okay, everyone. Good morning again. Actually, I wanted to begin by making a comment. As I mentioned a couple of times, I'm going at roughly half the pace that I was planning on for these lectures, which means that even though I had a sort of complete story that I wanted to tell, that would have by today gotten us to actually talking about E plus E minus colliders and proton-proton colliders and muon colliders, maybe, is instead putting me today in the middle of finishing a rather hopefully interesting but sort of formal set of topics about the inevitability of the laws of nature. So I want to make the following comment. If there is any of you who are actually interested in the sort of last part of this discussion, as well as just sort of more generally more of a conversation about some of these questions about what's special about the Higgs, what the hierarchy problem really means, etc. What I'd like to do is the following. Those of you who are interested in this, please feel free to send me an email, the following week is a little bit crazy for me, but the week after that is more or less open. And so I encourage all of you to just, who are interested, if there's a time in not next week, but the week after next, that works for you to be able to sort of get together for some informal continuation of these lectures, just email me. And what I'll do is just whoever emails me, of course, zero pressure, but whoever emails me, I'll sort of collect. Just email me with some dates in that week that don't work, or maybe better, some dates in that week that do. Then I'll try to take an overlap of whatever the group of people who emails me is, and I'll take the overlap of as many of the dates that work as possible. And I'll make a proposal for a day of, maybe a couple hours or a more open-ended set of discussions after that, so that we can properly finish what, or at least somewhat properly finish what I had planned to actually get to in these lectures. So anyway, zero pressure. People who don't want to do it, obviously, I'm not gonna force you, and it's all very anonymous anyway, so it's not like I'm taking notes about who is and isn't showing up. But if you do want to have this discussion, do send me that email. I'll go through everything. I'll overlap the lists, and then we can do this not next week again, but the week after next. Okay, yeah. And so my email address is just you can also see it on the web, but it's just arcani@ias.edu. Okay. Okay, so I encourage you to do that. Again, just send me an email with what times, not next week, but the week after next might work for you. Hopefully, if you can say what those times would be, if you can translate them to Eastern time, my time, so that I don't have yet another opportunity to screw up, that would be great. And then we'll arrange this to happen. Okay. All right. Thank you very much. And okay, so let's get to it today. Remember, what we're trying to do is understand something about the possible consistent theories of massless particles. So what are the consistent theories of massless particles that we can have? And our sort of journey so far has been in lecture 2, roughly speaking, we learned what are massless particles, how do we think about them? In other words, they are irreps of Poincare, and they turn out to be labeled by helicity, in addition to momentum. And in lecture 3, last lecture, we talked about what you might have thought of as the sort of first non-trivial interactions could be, which are when we have massless particles with helicities h1, h2, and h3. We worked out that these guys are determined, fully determined by, the structure is fully determined up to strength, up to coupling constant by Poincare as well. So despite the fact that, so this begins to look like it depends on, maybe you have to choose a Lagrangian, or, talk about how you're going to write down the fields and contract all the indices and all that kind of stuff. In fact, it's also totally determined just up to the strength of the coupling constant by Poincare. And we started doing this by introducing also the spinor helicity variables for massless particles. Okay. This representation, on the one hand, makes it manifest that P is null. This guarantees that P squared is equal to 0. But on the other hand, precisely because under lambda goes to T lambda and lambda tilde goes to T inverse lambda tilde, P goes to P, we discovered that this is in fact the simple action of the little group. And therefore amplitudes are really functions of lambda and lambda tilde. So just if we have an amplitude for n particles, massless particles with helicities, with momenta labeled by spinor helicity variables lambda and lambda tilde and helicities HA, then the group theoretic property of this is that one, it has to be a function of only these sort of brackets like lambda I, lambda j, which we called ij, or lambda tilde I, lambda tilde j, we called the square brackets ij. So these are the only Lorentz invariants that we can have. But two, it has to have a particular so-called helicity weight. So if I rescale the 8th particle by TA and TA inverse for their lambda and lambda tilde, the whole amplitude has to pick up a weight given by TA to the negative 2HA. Okay, and this now contains all the information, the kinematic information that we have about massless amplitudes, and the fact that when you do a Lorentz transformation on the momenta, they have to pick up a little group phase. As we discussed, those things are not are only redundantly described by polarization vectors and momenta for massless particles, because the polarization vectors don't exist. They only exist up to something shifted by the null momentum of the massless particle, but they're directly functions of the spinor helicity variable. So, as I said, if you've taken a field theory course, you've probably never actually seen an amplitude before. You've seen some expression with things dotted into polarization vectors, but you've never actually seen the actual amplitude. You can actually see the actual amplitude when we work with these spinor helicity variables. Okay, so And to remind you where we got to when we have this nice expression when the helicities are H1, H2, and H3, this is equal to some coupling constant G times 1, 2 to the H3 minus H1 minus H2, 2, 3 to the H1 minus H2 minus H3, 3, 1 to the H2 minus H3 minus H1. And this expression is valid when the sum of the helicities is negative and some other coupling constant with the other kind of bracket and with the exponents reversed. Okay, so when the sum of the helicities is positive. Okay, so now we're going to move on. So this really completes the essentially kinematical part of the story. So now we're really going to move on to interactions more interestingly. We're going to talk about the 4-particle amplitude. Okay, so there's some amplitude now for 4 particles. And before doing anything fancy, let's just go back. Let's remember things we know just from you know our simple courses. So so let's say that we had an underlying phi cube theory. Then you know that at tree level, the amplitude would just be the sum of these diagrams, right? Okay, 1. So this we often call the S channel, the U channel, and the T channel. And the corresponding expressions would be that this would be, if the strength of this coupling constant there is mu, this would be mu squared 1 over S plus 1 over T plus 1 over U. Or the way I wrote it there, plus 1 over U plus 1 over T. Again, where as usual, S is P1 plus P2 squared, which for massless particles would just be 2p1 dot p2, and U would be p1 plus p3 squared, 2 p1 dot p3, and T would be p2 plus p3 squared. And from now on in this lecture, I'm probably going to very often be sloppy about these factors of 2. Okay, so okay, so that's what the amplitude is. In this case, quite trivially, we see from the Feynman diagrams. But I want you to see from here that let's say that I mean, in this case, it's so simple. We just computed the Feynman diagrams. We just did it. But there's a way that you can check whether the result is right or wrong, even if you hadn't done the computation. Okay, and the reason is that that this 4-particle amplitude in this approximation, where the amplitude only is at tree level, when the amplitude is at tree level, it has a very simple structure, right? The only singularities that it can have are poles. By the way, it could have, of course, there could also be pieces. I mean, I might have had a 4-particle amplitude too, right? In other words, I might have had a phi to the 4 coupling. So that would have just been some a constant, okay? Or even maybe I have a d phi to the 4 coupling. So I might even have some correction that goes like S or T or U, okay, times some other coupling constant, or S squared, T squared, U squared, times some other coupling constant, and so on, okay? So these are all things that are polynomials in the momenta. And okay, so whatever the couplings are in the theory, I'd have to have, I can certainly have these polynomials. I can have as many of them as I like. But if there was a phi cubed coupling, the very presence of the phi cubed coupling means that the amplitude has to have something which has a pole in it. It can't just be smooth as ST and U goes to 0. It has to have a pole in it, and the pole corresponds, of course, just to the exchange that we see in these diagrams. Okay, so if there is a phi cube coupling, in other words, the very fact that we have this coupling means that the amplitude has to have a pole. And note that this is true at tree level. We know that we could have more complicated singularities than poles once we go to loop level. For example, at loop level, I could have something like this. And these diagrams can have logarithms in them. They can have things like logarithm of S, even more complicated functions of S. But we're going to be working at tree level. And you might ask, what do I mean by tree level? I keep talking about the fact that we want to talk about things without talking about fields and Lagrangians and Feynman diagrams and so on. And then all of a sudden I'm saying the word tree level. That sure sounds like I'm thinking about Feynman diagrams. But in fact, what tree level means is a little bit more invariant. Tree level is reflecting what kind of singularities the amplitude has. Okay, so we can sort of reverse it. We can say that the amplitude could be completely smooth, okay, at 0 energies. So that's just having polynomial interactions. That's the simplest possible analytic structure. The simplest possible case is it has no singularities at all. At least no singularities at 0 energies. It would have singularities at infinite energy, but no singularities at low energies. Okay, so no singularities here at low energy. The next simplest kind of structure it could have is to have poles, and then that does have a singularity. And then after that, the next most complicated structure of that would be to have a logarithm which has a branch cut. Okay, so if I think in the complex S plane, I can have a pole at S equals 0, for example, or I can have a branch cut that would correspond to a log. Actually, the branch cut is here. This is in the S plane. And then these could get more and more complicated. As we go to higher and higher loops, this would get more and more complicated. But we're going to imagine that there is some kind of weak coupling between the particles. After all, we're talking about a scattering amplitude. So we imagine the particles are escaping to infinity. And that means that we're going to restrict ourselves to the case where there's only poles. Okay, so that's an approximation. But in the approximation where there's only poles, when we get things from Feynman diagrams, that's tree level. But you can think of it more invariantly as we're organizing the amplitude in how complicated the singularities are. And so we're beginning with the simplest possible singularities where the only singularities are poles. Okay. So let's say that we've done that now. So now what we're doing is we're talking about a 4-particle amplitude, okay, and where it can only have poles. So again, this is quote unquote tree level. And now there are two physical requirements. And these two physical requirements are inputting the physics of locality and unitarity in the answer. Okay, so these are the constraints that we're now going to talk about. So one, locality says that the amplitude should have simple poles. Only simple poles that go like 1 over s or 1 over t or 1 over u as s and t and u goes to 0. All right. So what are some things, examples of things that are not allowed? I cannot have 1 over s squared or 1 over s cubed and so on. Can't have that. I can't have 1 over st minus u squared or more complicated things like that. I mean, if I'm just writing down random formulas with poles in them, these are all kinds of things that I could have. No, the only kind of poles that I'm allowed to have are just 1 over s, 1 over t, and 1 over u. Okay, so these are the only allowed poles. And this has to do, again, this reflects something that we're intuitively familiar with, that where are these poles coming from? These poles are coming from the fact that that normally the amplitude is smooth, but the poles can occur when you can produce some intermediate state. And the intermediate state, this is in position space. The intermediate state propagates a long distance and decays out somewhere else, okay? But in order for this to be what is happening, so where this is a long distance, all right, the image of this back in momentum space is that in momentum space, we have to have a 1 over, so if this momentum is capital P, we have to have 1 over P squared, which is literally the propagator of this particle, right? Okay, so that says that the pole corresponds to the propagation of a particle over a long distance. All right, so that's requirement number 1. Let me say it again. So here I have my 4-point amplitude, and requirement 1 is that it should only have poles, and only simple poles, as s, t, and u go to 0. Now, requirement 2, and so this is locality of interactions. Yeah, Max, go ahead.
Yeah, hi. I can ask you some more thing about this relation between locality and simple poles, because so if I think of a pole like 1 over p to the 4, then I usually think of that this describes maybe 2 particles. One of them is a ghost. So and so can I use this intuition to understand why this would be a non-local theory in some sense?
Yeah, I mean, so in fact, if you just hang on a second, you'll see that this is very closely related to the second point. And this is, by the way, it's kind of already we see in this very simple example, kind of a fascinating relationship between these two notions of locality and unitarity. They're not totally decoupled from each other, and it's very much related to what I'm about to say. You see, one way of phrasing what's wrong with the 1 over, it's obvious that the 1 over st minus u squared is crap. Okay, that doesn't mean anything. But you're right. You could say, well, what about 1 over p squared squared, or 1 over p squared to the 4th? From the perspective of the Lagrangian, as you say, you can think of them as a pair of particles with opposite signs in the propagator. So what's going on there is that the residue on p squared equals 0 is actually vanishing. And it's vanishing because there's something with a plus sign and something with a minus sign. Okay, so that's how you see that it's violating that we can't interpret the produced particle as having produced something with positive probability. Okay, so and that's actually just the second point I'm just about to come to, which is to give an interpretation of what the residues on the poles are as ST and U goes to a 0. So if you like, I could say that maybe I'll allow things that have higher powers of ST and U, but that'll now be killed by my second requirement that I'm just about to talk about. Okay.
Okay. Thank you.
Now, so what is the second requirement? Is that, let's say on the pole as S goes to 0, say, I should be able to see that the amplitude there goes like 1 over S, that's my pole, but then I should be able to interpret in the neighborhood as S goes to 0. See, the whole point is in the neighborhood as S goes to 0, this intermediate state is now on shell, right? That intermediate state is now on shell. So I have to be able to interpret the residue as that I just produced a particle here. And then the particle produced went a distance and it made the other guys. Okay, so that means that and if here it has helicity H and it's outgoing, on this leg it would be incoming with also the helicity H, but if I since I'm labeling everything with incoming momenta, this would have to be helicity negative H. Okay, so in other words, if I say it more technically, the residue of the pole as S goes to 0 has to be interpreted as the product of 3 particle amplitudes summed over everybody that can propagate in the middle here, whatever the states are, give them some label A, and with helicities H and negative H. Okay. And you see, that's cool because we just learned that these 3 particle amplitudes are fully fixed by Poincare symmetry. So now we can begin to see that that we have a constraint. We have a sort of we have an interesting constraint that the 4 particle amplitude is forced to have poles because there are 3 particle amplitudes, but on those poles it has to factorize into the product of 3 particle amplitudes in the appropriate way. Okay, so that's it. These are my two requirements. Let me summarize again. M4 should have just simple poles as STU goes to 0 at most. And 2, on those poles, we need to have factorization. That the residue, let's say as S goes to 0, so we get 1 over S, but then we should be able to interpret it as the sum of anything that's propagating between them. But now these are on shell, okay, with helicity H and negative H. Okay. And again, 1 is somewhat loosely locality, and 2 is unitarity. All right. So now that is our task. So now we have we're starting to have a well-defined task. So for instance, let's go back to our example where the amplitude was 1 over S plus 1 over T plus 1 over U. This is an extremely simple example. Okay. And let's see what happens as S goes to 0. Well, we have 1 over S times mu squared. And indeed, this 3 particle amplitude was mu. That other 3 particle amplitude was mu. So mu squared is mu times mu. And so indeed, this amplitude works. Great. Okay. Let me just show you one more example. Let's say that let's look at another. So that's a phi cube theory. Let's look at a Yukawa theory. Okay. So here's let's write what a Yukawa coupling looks like. We didn't do that example last time, so let's do it. Let's do it now. So let's say I have a massless fermion now of helicity -0.5 and a spin 0 particle. So this is some phi. So this is some fermion psi. This is some spin 0 particle with helicity 0. So if this is particle 1, 2, and 3, then by our rules from last time, what is the amplitude? Well, you can shove it into that general formula, or I can just write it down, and you know there's a unique expression with the correct weights. So all you have got to do is write the expression with the correct weights, even if you don't remember the formula. And okay, that's the expression. Okay. Very good. Okay, so and notice that, remember, this was supposed to have units of mass. So from here we see this already has units of mass, so we see that y is dimensionless. Okay, so that's just like what you expect for a Yukawa coupler. All right. And so let's say we want to have a 4-particle amplitude now, where let's say all of them are minus for fun. Okay, so particle 1 is minus, 2 is minus, 3 is minus, 4 is minus. Okay, so what's the amplitude? Well, I'm just going to write down the answer right away. It's y squared times 1, 2 times 3, 4 over s. Okay, and let's see why it's correct. Okay, so this is a slightly more interesting example. Now I only have one channel here as s goes to 0, but as s goes to 0, this looks like 1 over s times this 3-particle amplitude, 1 minus, 2 minus, phi, and then there's a phi, 3 minus, 4 minus on the other side. Okay, good. So this was y times 1, 2. This was y times 3, 4. And so lickety split, we've written down the amplitude for scattering of fermions through a Yukawa interaction. And I hope you're already maybe slightly impressed with this, because we didn't have any gamma matrices, we didn't have any, U bar, V, all that crap that I certainly never remember how to think about it, okay? Without looking it up, the conventions in some book and gamma 5 and all that junk. We never see any 4-component anything here. Okay, we just wrote down the answer, all right? Okay, and in fact, I encourage you to do an exercise. Try to write down the 4-point amplitude for like a Compton scattering in this example, like where it would look like phi. So let's say something like this. So 1 minus 2 for the phi, and then 3 for the phi, and let me do like 4 plus. Okay. Let's actually see if we can do this example ourselves. Let's see if we can do it now, because this gives us a good. This should also give us a good. It'll give us a template for what we're about to start playing with. There is a question in the chat whether we have the other channels as well. I don't necessarily have to have the other channels. It could be that this was the only. In other words, these particles 1, 2, 3, 4. They might be different species of particle. So that this is the only. So the only coupling I have is of 1, 2 to phi and 3, 4 to phi. But I don't necessarily have to have a coupling of 2 and 3 to phi. If I did, I'd have to include the other channels too, and then you would do it. Okay. So let's say that, in fact, let's say that all of these guys were identical. Okay. If all the fermions were identical, then indeed I would have to add the other channels. So I would have to write something like 2, 3, 1, 4 over T, and have add the other ones as well. Okay. So you can also finish doing that exercise. But let's look at this one, and we can start seeing a strategy for writing down the answer, because it looks simple, right? It looks like as s goes to 0, what should the residue be? Okay, what should the residue be? Well, as s goes to 0, well, let's just write it down. It would have to be this product of 3-particle amplitudes. Okay, so this would be 1 minus and some intermediate minus here. And this would have to be the same intermediate plus. And that's why I put a plus here. Okay, so if I put a plus here, then here I can have 4 plus, let's say. And And so this this would be a different coupling. Okay, so if I write down the kind of couplings that I'm allowed to have, we could have the one that we wrote down where it's 1 minus 2 minus phi, and that would be some y 1 2. I could also have some 1 plus 2 plus phi, and that could be even some different y prime times the square bracket for 1 2. And notice that that y prime doesn't have to equal y, which means that we don't have to respect parity. Okay, so if so let's go back to this example now. Let's work out what the residue is over here, and let's try to do it a little bit carefully, because on this side now we are encountering something slightly new. We've got to worry about this intermediate guy. Okay, so on this side, on the left, I have something like, so let me write it big again as s goes to 0. I have 1 minus 2 intermediate minus intermediate plus 3 4. So on this side, on the left, I have a residue which is y 1i. On the right, I have y prime I 4. Okay. And so this is now slightly cool, because what is it how do I figure out what this is? How do I figure out what this product is? 1i I4. By the way, notice something nice here, that there is no little group weight under I, right? And that's good, because the answer doesn't, on the outside, doesn't know anything about I. It should only have little group weight under the external particles, and that's good. That the I occurs here with an angle bracket and a square bracket, so the little groups cancel on the inside. And that's the reason. That's another way we can see that we have to add a minus here and a plus there. That's the only way that the little group weights can cancel between one leg and the other leg of the I. But how can we figure out what this is? Well, we just have to remember that pi is actually equal to lambda I tilde, right? So this is a massless particle. I is a massless particle. The whole point is that it's on shell. So pi alpha dot is lambda alpha I, lambda tilde alpha dot I. So what is this expression? This expression is lambda 1 alpha p intermediate alpha dot lambda tilde 4 alpha dot. If for once I write it out explicitly like this, we can also write it as 1 p intermediate 4. Okay, so I hope that notation is clear. All right, but now we're going to write p intermediate is equal to p1 plus p2. Okay, I could also write it as negative p3, negative p4. These are two different ways that I could write this p intermediate. And so therefore p intermediate lambda 1, let's say I chose this expression. This is equal to 1 p1 plus p2. But the point is that the p1 part cancels. Why does the p1 part cancel? Because p1 is massless, right? So p1 alpha dot lambda 1 alpha, this is equal to 0 because p1 is lambda 1 tilde, right? So the lambda 1 is giving me 0. Okay, so from here I see that 1 p intermediate 4 is equal to, in fact, 1 2 4. So I could write this as 1 2 2 4. So that's a nice expression, right? Because p2 itself is massless and is lambda 2 tilde, right? So I could have also written it as 1 negative p3 negative p4 4, and now the p4 part goes away, and this would be negative 1 3 3 4. So this is something we're going to see over and over again in the four-particle kinematics is expressions like this. So that when we have this guy, this is the same as 1 P2 4, which is the same as negative 1 P3 4. And so I could write this many ways. I could write it in a more symmetric way between particles 2 and 3 with a 1/2, 1 P2 minus P3 4, for example. Okay, so these are all equivalent ways of writing it, all the support of momentum conservation. All right. But anyway, one way or the other, we've now learned what is residue. Okay? We've now learned that this residue is phi 1 minus 2 intermediate minus intermediate plus 3 4. Let's even just choose one. Let me even just write just in terms of 2. Just is like 1 2 2 4. Okay. So it looks like life is easy. That's what the residue has to be when S goes to 0. So the answer has to be, the amplitude has to be 1 2 2 4 over S. Done. Okay, with a y prime. Okay, so there's a y and a y prime here. So times y prime. Which again, if I wanted to write it more symmetrically, I could write as 1 P2 minus P3 4. Okay, over S. Maybe with a 1/2. All right. Any questions about this? Go ahead, Fabio.
Hi, just to be sure, all contractions are done with the epsilon tensor, right?
All contractions are always done with the epsilon symbol. That's the only tensors we have here. That's right.
Yeah, okay. Okay, right, thanks.
Yeah.
Gautam?
Okay, so what would happen if we introducing a pole as 1 over S, if we had like the U channel, how would that look like?
Oh, what do you just repeat exactly the exercise? You want to do it? Okay, so we can do yeah. So let's say it looked like this instead, right? I mean, just the U channel in this case would just literally be reversing particles 2 and 3, right?
Right. So it'd be P3 minus P2, I'm assuming.
Yes, that's right. Exactly.
Okay, and so would the final amplitude be some linear combination of S and U? Because
yeah,
that
that's
would
right.
still follow
exactly. We'd have
of...
to have a pole in each one. Exactly. So if these scalars, were identical, then I would have to have the other channel as well, and then I would add those two channels. Exactly.
Okay, great. Thank you.
Yeah. Okay. Any other questions? Yeah, I'm just doing one of the residues at a time. In fact, shortly we're going to be talking about more than one residue at a time for a reason that will become obvious in a second. Maria, you had a question.
Hi. I have a question that goes back to the reasoning about the poles of the four-particle amplitude.
Yes.
Like we know that it has poles when you perform the canonical calculation with the Lagrangians and so on.
Right.
But using your argumentation line, I think I got lost. Why do you deduce that it must have poles?
Well, I think there is a longer answer to this question, but the shorter answer, and maybe the sort of best answer right now, is that on quite general grounds, we don't know a priori what the analytic structure of the amplitudes actually has to be. Okay, so part of the little bit of the art in this subject is to just from what we know. You see, what is the basic problem? The basic problem is that the amplitudes are something that you measure from far away. Okay, so the sort of the data that labels a process is some things that come in, something scatters, and they go out, right? And all you have access to is what happened at infinity, the infinite past and the infinite future.
Yeah.
What we're trying to figure out is what property of this answer somehow encodes that it could come from a process that could be given a local description if you wanted to, okay? Now, we know that if you do start with a Lagrangian and so on, then that will certainly be the case. You're giving it a local description. So what you try to do is look at what the answer looks like, but not in detail. Look at what just some of the gross features of the answer looks like that you get when you start from a Lagrangian, and try to use that to sort of guess what the more abstract properties are that you could impose on the answer that carries the fingerprints of that property of locality that you wanted to. Okay, so you could say that this zeroth order is kind of cheating a little bit. You look at the answer and you go back and say this is what you want. In this case, there's slightly better answers to your question, but not that much better. And it would take a lot longer to explain those very slightly better answers. So just right at the moment, just think of it this way. It's like, we don't want to compute the Feynman diagrams. We're lazy. We don't want to do all these horrible things and some polarization vectors and all that stuff. We're enjoying seeing how directly we can determine all these things, but somehow we can write down a million formulas that are not what we get from when we play with Lagrangians and Feynman rules. So we just want to sniff a little bit, just a little bit of information from what we get from Lagrangians, which is just the kind of pole you have, and then say, okay, that's all I need from you. Go away now, and then we try to impose those conditions and see how far we can get. Yeah. So your question's a very good one. And while at tree level, I can give you a slightly better answer, when we get to loop level, we really can't, okay? And so one kind of looks a little bit at what the kind of functions are, what the kind of analytic structure is, and then you go back and pretend that you didn't look and just try to impose that and see how far you can get, okay? In the end, there's the most adventurous answer to this question is that ultimately what we're doing now is trying to impose consistency conditions to determine the answer, okay? But those consistency conditions partially are coming from thinking about maybe these things came from Lagrangians after all. The most sort of intellectually exciting part of this whole program is to try to sever that tie totally, right? And just try to think about the amplitudes as the answer to some completely different question. If we eventually find the amplitudes, even for general scattering problems in the real world, if we can find them as the answers to radically different questions, then the nature of that question would tell us what kind of pole it's supposed to have, what kind of singularity it's supposed to have, and so on. And then we would read backwards from that, very likely quite abstract seeming question, why we are forced to have all these properties that we then ascribe to locality and unitarity, having space-time and quantum mechanics and all of that. But we're not talking about that at all, right? That's a much more speculative part of this subject. I think an exciting part of the subject, but much more speculative part of the subject. Here we're just trying to impose consistency conditions. So as I said, we have to sniff a little bit what's going on from the answer, and then say, okay, that's all I need from you. Go away, and we continue.
Okay, thank you.
Okay, all right. Any other questions?
Julian?
Yes, so sorry, I may got lost somewhere, but is there an easy way to understand when, like, which, or an intuitive way to understand, like, when to take which vector parallel, which not? So when to use the which bracket?
Yes. We had that rule. The rule is when the sum of the helicities is negative, you have to take the lambda tildes parallel. And then the amplitude is only written in terms of the angle brackets. And when the sum of the helicities is positive, it's the other way around.
Okay, sorry. Maybe have missed that. Thank you very much for clearing it
Yeah.
up.
And let me just remind you why that is. Okay, so just with an example. So if it was like 1 minus 2 minus 3 plus, there are two expressions that we can write down. 1 2 cubed over 1 3 2 3, or the reverse, 1 3 2 3 with the square brackets over 1 2 cubed. Okay, these are two expressions with the identical helicity weights. But as we go to Minkowski space, so remember in Minkowski space, everybody becomes parallel, because if this is the configuration where the lambda tildes are parallel, but in Minkowski space, that forces the lambdas to be parallel as well. Okay, so as we go towards Minkowski space, everyone is forced to be parallel, but then this guy goes to 0, but that guy goes to infinity. Okay, because as the lambdas become parallel, there's the upstairs is vanishing like the cube, the downstairs is vanishing like the square. Okay, so it's that requirement which tells us that when the sum of the helicities is negative, we have to write things in terms of these brackets, and when it's positive, we have to write in terms of those. Okay, did that make sense?
Yes, thanks a lot.
Nima, one question. Yesterday you mentioned that when the sum is equal to 0, still one can show it's inconsistent. Can you give a gist of how I?
You will see a gist of it. In fact, I'll leave that as an exercise for you after you see what we do in the other examples. Okay.
Perfect. There's a question in the chat by Oscar.
Yeah.
Who says he's asking about the sum over intermediate states.
Yes. No, it's not always a multiplicative factor. I mean, here we've just done, it's very simple examples with a few states. You know, you have to sum, you know, in total generality. I mean, if I want to say it stupidly, abstractly, we have, you know, a bunch of labels, helicities, and also labels A3, and you just have to sum over all of them, right? So it's a sum over all of these intermediate labels that you could possibly have, and some coupling constant here, G, A1, A2, A3, okay? So you really would have to have, if you have 1, 2, you'd have to have the sum over G, A1, A2, B, G, B, A3, A4, okay? So you really have to sum over everyone. Yes, and there's another question. This is just looking at the tree results for the amplitude so far. You can now start pursuing this philosophy further to get to a loop level as well, but here we're just doing trees. Maybe you're not so impressed yet. I mean, I'm sufficiently technically incompetent that I'm already impressed that I could write down these Yukawa Coupling amplitudes in 30 seconds without worrying about gamma matrices and stuff like that. But if you're not impressed now, you'll be impressed momentarily. I promise. Or you'll never be impressed. So, you know. Okay, shall we take a little break?
Sounds good. So let's come back in 5 minutes.
5 minutes, perfect.
Perfect.
Looks like a really nice day out there, Giovanni.
Yes, not bad.
I literally hear birds singing in the background. I mean,
Sorry.
No. Oh, it's great. It's very idyllic sounding. You know that we've been under attack here. There's a 17-year cycle of these insects, cicadas. It's unbelievable. I'd never experienced it. It's literally biblical. I mean, it's really, I mean, literally. You know, it's like it wasn't enough that we had the plague. Now we have the locusts. So, yeah.
What's the period again?
17 years. Every 17 years. Yeah. And you know, I like animals. I like creepy crawlies. I have no problem in general. But these things are a disaster. They're like, they really drive yeah. So.
For how long it lasts?
Birds in the back, you know, you have birds in the background. We're now at the peak of it. It's going to last another couple, but at the peak, when you go outside during the day, it's deafening. They're so loud. It's literally deafening. So you have to close all the windows. Even in the middle of the night, you close all the windows, everything. You can still hear them through the window. So this sort of sound of just one lone bird tweeting in the distance is very, you know, it's like paradise compared to what we're going through here. Right.
All right.
All righty, do. Shall we start back up?
Sounds good.
Oh, you want to hear the someone asked me to open the window so they can hear the cicadas. First, it's not quite as loud now, but secondly, much as I would love to entertain you, there's a really highly non-trivial chance that in the 20 seconds I would leave the window open, there would be 20 of them in here. And my wonderful cat, who's the best cat in the world. I apologize to anyone else who has cats that they think are great. They're not as great as my cat, I promise you. My cat has spent the past 4 weeks dispatching them, but she's exhausted downstairs right now from dealing with them. So I apologize. I'm not going to, you know, I'm not going to, just for the sake of your entertainment, I'm not going to put further hardship on my beloved gateau. Okay, I hope that doesn't strain our friendship permanently, but okay, very good. So, so now the excitement is going to begin, and in order to see what the excitement is, there's actually something interesting there's an interesting pattern we can observe in the 3 particle amplitudes that we didn't that, you know, we just wrote down the answer, but we haven't stared at quite enough of them. So I want you to notice an interesting difference between the 3 particle amplitudes for different kinds of theory. So let's look at what I'll call boring theories to begin with. So boring theories are boring from the Lagrangian point of view. There are things like phi cubed or Yukawa, like phi psi psi. So they're boring in that you don't need any fancy things like gauge symmetry and stuff like that to talk about them, okay? In fact, we just did these 2 examples. What do their Lagrangians look like? Okay, so sorry, what do their amplitudes look like? Well, this one was easy. This one was 1, 2, 3, was just given by mu. And this one, as we just said, is like 1 minus a half, 2 minus a half, and 0 was given by y times 1, 2. All right. But now let's look at exciting theories. So for example, let's look at a coupling of even the simplest thing of a charged scalar to a photon. Okay, so there's some spin 0 guy here. So this is spin 0, 1, 2, and massless spin 1, let's say with negative helicity, 3. Okay. Well, once again, we can write down the same we can write down the general formula, or we can just write down an answer here that has the correct weights. So so the answer that has the correct weights, it has to have weight 2 in particle 3. So it's 1, 3, 2, 3 divided by 1, 2. Okay, and there's some E here. Okay, and you can see that this thing already has units of mass, so that E is dimensionless. Okay, so there's already something kind of cool here, right? Which is this 3-particle amplitude already has a pole in it. Isn't that funny, right? It's a 3-particle amplitude that has a pole. What the hell does that mean? Okay. Well, it's fine. You can ask, I can't reach this pole in Minkowski space. In the real momenta, I don't see it because the whole amplitude is 0. Okay, there is more things upstairs than downstairs, but it's kind of interesting that this amplitude actually already has a pole in it. Let's look at the same thing with gravity. Okay, so what if this was now coupling to a graviton, so something that had helicity -2? Then what would the coupling be? It would just be this 1, 3, 2, 3 over 1, 2 squared, right? Because that now has the correct weight in 3. And now, what are the units of this? This would have to have units of 1 over mass, so that's like 1 over m Planck. So that indeed, that's the coupling to a graviton. But you see that these exciting theories, they have the property, and by exciting, I mean these are the theories that in the usual Lagrangian way of talking about things, we need gauge symmetry, gauge redundancy, general covariance, diffeomorphism invariance, and so on. And the difference between the boring and exciting theories is exactly that the boring theories, their 3-particle amplitudes are totally only numerators. There's no poles in them. But the exciting theories, the 3-particle amplitudes have poles in them. Okay, so that's just observe that interesting difference. So far we've only talked about cases like this. And now, why does it matter? Because remember, what did we do? We thought it was super easy to build 4-particle amplitudes that were correct. All we have to do is look at, I mean, this was our strategy, right? We say, look at the residue in the S channel, whatever it is. So there's some residue RS in the S channel, and similarly, RT in the T channel, and RU in the U channel. Maybe some of these are 0, but anyway, we have these residues. And then we say, good, the amplitude is just RS over S plus RT over T plus RU over U. Okay, that was basically our strategy so far, right? Just look at what the residue is, get the answer, and just slap on a 1 over S in front of it. But now you see what the problem is. The problem is that when the 3-particle amplitude itself has a pole, then when you compute the residue in the S channel, the answer could well have a pole in another channel, right? So that if you write the expression RS over S, you might not be free and clear, because that expression that you wrote down might now actually have a singularity somewhere else that you have to go check if that works out correctly or not. Okay, and we're going to see precisely that this is what actually happens. Now we could do many examples. I'm not going to do all of them, but I'm going to do some sort of canonical ones. So I'm going to begin with imagining, can we have a single particle of spin S? So I'm going to, since there's also the S channel, I'll write the spin as curly S. So, but there's just one particle. I'm going to imagine that it has this 3-particle interaction, 1, 2, 3, so that this amplitude is some G, some coupling constant, 1, 2 cubed over 1, 3, 2, 3 to the power of this S. And similarly, there's some plus minus, which is G prime. Maybe I'll just keep calling it G. This part is not going to matter so much. The other kind of bracket, 1, 2 cubed over 1, 3, 2, 3. to the power of S. Okay. All right. And so now what I'm going to do is look at the 4-point scattering for this configuration. 1 minus, 2 plus, 1 minus, 2 plus, 3 minus, 4 plus. Okay. Now, just ahead of time, by the way, guys, just so we know what we're looking for, I know ahead of time, whatever this is going to look like 1, 3 to the power of 2s, 2, 4 to the power of 2s, and then what's left is going to be some function of the usual Mandelstam variables. Right? And why do I know that? Because if I pull these factors out, I've already soaked up all of the weights, right? I've soaked up the weight on particles 1 and 3. I've soaked up the weights on particles 2 and 4. And so whatever is left cannot have any weights, and that will be a function of the Mandelstam invariants, ST and U. Okay? So I know that ahead of time. We're going to see it explicitly anyway, but just so we're not, we knew that it had to come out in that way ahead of time. All right. So let's try our strategy and look at the residue in the S channel. Okay. So so there I'm going to get, so I have 1 minus, 2 plus, some, let's say, intermediate minus, then intermediate plus, 3 minus, and 4 plus. Okay, so the expression here is 1i cubed over 1, 2, 2i. And then on the other side, I'm going to get I4 cubed over I3, 3, 4. So this is to the S, and this is to the S. Okay, I'm not going to keep writing the coupling constants over and over again. And so if we use that 1i, I4, so this is the same thing that we saw in our previous exercises. 1i, I4 is 1 p intermediate 4. And so this is either 1, 2, 2, 4, or equivalently is negative 1, 3, 3, 4. Then we can simplify these. We can simplify this expression. So, for example, from the 1i, I4, I can replace that with the 1, 3, 3, 4 upstairs. Okay, so if I just write it out, like 1i cubed, I4 cubed. So this is what I'm staring at, right? Is 1, 2, I2, I3, 3, 4, all to the power of S. But this I can write as like 1i, I4. I can write, for example, as 1, 2, 2, 4 cubed. And down here, I can write it as 1, 2. And this I2, I3 here, I can write, for instance, as 1, 2, 2, 3. Or let me write it, yeah, let me write it as 1, 4, 3, 4. And so you can simplify this as just 1, 3 squared, 2, 4 squared over U, which is 1, 3, 3, 1, all to the S. Okay, so I'll write it again. This is 1, 3 squared, 2, 4 squared to the S over U to the S. All right, so the summary is that the residue in the S channel is equal to, well, remember, I promised that we'd have this factor 1, 3 to the 2s, 2, 4 to the 2s out in front ubiquitously, and it's now divided by u to the s. And similarly, we have the residues in the other channels. Okay, so the residue in the T channel would be the same 1, 3, always the same. Now, let's say over the S to the power of the spin, and the residue in the U channel would be over U, T to the S. All right. So you see what the problem is, right? If obviously if S equals 0, then everything is okay. All these residues are just all these residues have no poles. And so our strategy that M equals RS over S plus RT over T plus RU over U just gives me, G squared times 1 over S plus 1 over T plus 1 over U. And that's correct. That's what we did our very first example. But let's say that we now look at S equals 1. Okay, so if we look at S equals 1, then the residue in the S channel is 1, 3 squared, 2, 4 squared, multiplied by 1 over U. All right. And similarly, the residue in T is this thing multiplied by 1 over S, and the residue in U is this thing multiplied by 1 over T. All right, well, that's pretty interesting then, because if I'm going to attempt to make an amplitude using the residue, now you see the problem. If I just take RS over S, well, this is the stuff here times 1 over SU. And now this is going to have a residue in the U channel. And that residue in the U channel has got to be given by this thing with the T, and so on. Okay, so now I have a self-consistency problem that I have to deal with. Okay, so let's write down what the most general ansatz is that I could have that's compatible with this kind of residue that I'm seeing here. So what's the most general ansatz I could have? The amplitude could be 1, 3 squared, 2, 4 squared. Okay. Always factored out. This is always with spin equals 1. But I can have some A over ST plus B over TU plus C over US. All right. See, this is already kind of cool, because normally we think, oh, the amplitudes are just 1 over S plus 1 over T plus 1 over U, and this can't look like that here. Okay? It's got to look more interesting to even have a chance of reflecting this fact that we just talked about. All right, and let's see how it works. Let's see what happens as S goes to 0. Okay. So we want to see the residue as S goes to 0. And now here we have to remember that S plus T plus U equals 0. Okay. So as S goes to 0, T is equal to negative U. Okay. So as S goes to 0, I get a residue from this term, and I get a residue from this term. So what is the residue as S goes to 0? Is equal to A over T plus C over U, okay? Which I can write as, because T is equal to minus U, I can write this as C minus A over U. Remember, this is only supposed to be valid as S goes to 0, right? So we're only interested in as S goes to 0. So this residue is equal to C minus A over U. Okay, so beginning from this ansatz, we can work out what the residues are. This is the residue as S goes to 0. Sorry, and I'm factoring out this thing out in front. I'm not going to keep writing that over and over again. The residue as T goes to 0, similarly, is B over U plus A over S, which I can write as A minus B over S. And finally, the residue as U goes to 0 is B over T plus C over S, which is B minus C over T. And I'm writing it this way because remember what we worked out these residues had to be. This residue had to equal 1 over U, this had to equal 1 over S, and this has to equal 1 over T. So I have a constraint on these A, B, C. They have to satisfy that C minus A equals 1, that A minus B equals 1, and that B minus C equals 1. Okay, that's what we have to have in order to satisfy our rules. And you see, this is impossible. Because simply add these three equations. Add this plus this plus this. On the left-hand side, we get 0. On the right-hand side, we get 3. Okay. So very cool. We've discovered our first thing, which is impossible. I cannot have single self-interacting spin 1. And this is good because, as I mentioned at some point in one of the other lectures, if we looked at this amplitude, this 1, 2 cubed over 1, 3, 2, 3, this is here 1 and 2 would be fermions. Because if you interchange 1 to 2, the amplitude goes to negative itself, and yet the particles have even spin. Okay. So it's a good thing that we didn't find a consistent theory here, because that would have violated spin statistics. Okay, so good. It's good that that our rules are telling us that this is not actually allowed. Okay. Okay. So what can we do? Well, let's now imagine we have multiple spin 1. And let's go back to this picture where this was 1 minus, 2 minus, 3 plus, and I'll decorate this with an A, B, and a C, or maybe I'll call it A1, A2, A3. Be more professional. So A, oh, damn it. So I'm going to now introduce something. Oops. Now a new object here, FA1, A2, A3, and still the 1, 2 cubed over 1, 3, 2, 3. Remember, this is now just for spin 1, all for spin 1. Now we don't have to do anything, any extra work other than just decorating some indices here. So when we have this object, now we're going to say that the most general ansatz is 1, 3 squared, 2, 4 squared. And now we're going to have some A, which has these 4 indices on it. So A1, A2, A3, A4 over ST plus B, just exactly what we had before, just putting 4 indices on it. Whatever we called it before, SU. All right. And when we go through the residues, it's exactly the same formula as before. Remember, before we said we had to have C. Oh, but sorry. But now, what does the residue have to equal in the S channel? It's exactly all the angle bracket stuff is the same as before. But what is the dependence now on these indices? So here, if there's some intermediate E, this would be F A1, A2, E, F, E, A3, A4. Okay? So going through exactly our same argument as before, from the residue in the S channel, we would discover that C, beforehand we had that C minus A equals 1. And then we had that A minus B equals 1. And then we had that B minus C equals 1. But now instead of 1, we're going to have C A1, A2, A3, A4 minus A, A1, A2, A3, A4 has to equal some F, A1, A2, E, F, E, A3, A4. And then we're going to have another F, F, and we're going to have another F, F here with the appropriate things here and some E. Okay, I'll leave for you to fill in just fill in those indices, but I think it's clear to you what it'll look like. Okay, and so now, how do we avoid a contradiction? Before we got a contradiction because when we added these three equations, we got 0 on the left-hand side, but on the right-hand side, we had 1 plus 1 plus 1, which was not 0. But now we're not going to have 1 plus 1 plus 1 anymore, are we? What are we going to get on the right-hand side? So in order for these equations to be consistent, as someone said already in the chat, we have to have that F, F plus F, F plus F, F with something, something E, E something, 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 something E, E something, 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 something E, E something, something equals 0. And where have you seen this before? This is the Jacobi identity for a Lie algebra. It tells you that the F A1, A2, A3 must be structure constants. Which furthermore tells you from general things, you know that FABC have to be antisymmetric amongst other things, which then solves the Bose symmetry problem of the amplitude, okay? So as I said, I hope you're impressed with this. Again, in some of the usual ways of talking about Yang-Mills theory, it's all about the beauty and how lovely it is that we can rotate the phase far away. We can rotate the phase here and there independently, and because it's so elegant and pretty and blah, 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 blah. But you see, nothing to do with elegance or pretty or beauty, zilch. It's nailed on you. You can do nothing about it, okay? The only way to have a consistent theory of massless spin 1 particles is for the interaction to be governed by the structure constants of a Lie group, okay? I think that's an absolutely amazing fact. All right, let's keep going with our exercise. Let's keep going and go to spin 2. Spin S equals 2. Now, if we look at the residue in the S channel, then we're going to get 1, 3, 2, 4 to the 4th. But remember, our formula was 1 over U to the S. So now this would be 1 over U squared. So this would be 1, 3, 2, 4 to the 4th, 1 over U squared. And now naively you think we're dead, right? Because this residue is 1 over U squared. And therefore, if I write down anything I write down would have to be, the amplitude would have to be, 1 over S times 1 over U squared times this 1, 3, 2, 4 to the 4th. And this has a double pole, which we're not allowed to have. So it looks like we're dead, except you have to remember this residue, when we say it's 1 over, when we say that the residue as S goes to 0 is this thing to the 4th times 1 over U squared, this is only valid when s equals 0. And remember, when s equals 0, u is equal to negative t. So we could equally well have written this as 1324 to the 4th times, with a minus sign, minus 1 over tu. And that few has simple poles and just t and u. But now, if that's what we're going to do, there's a unique thing the answer can be. The answer has to be, with a minus sign, 13 to the 4th, 24 to the 4th, over s times t times u. Exactly, Oscar. That's it. And you see, now we're done, because now by symmetry, when I check the other channels, it's also going to work. So we're done. There is a consistent theory of the massless spin 2 particle. And not only have we confirmed that the theory exists, but we just computed the amplitude for it. Okay. So this is the 4 particle amplitude for gravitons. Right? And the coupling constant out in front is 1 over m Planck squared. Okay. So this is the 4 gravity amplitude at tree level. And as I said in an early lecture, good luck if you try to do this calculation using Feynman diagrams. Okay. Already the 3 particle vertex is like 100 terms in it. And this is the most nightmarish calculation that you could do it with the computer, but you can't do it by hand. And indeed, as Oscar says, this was done in a tour de force amazing calculation by Bryce DeWitt in the late 1960s, early 70s. I don't remember exactly what, but around then. All right. So so we discover that that we are allowed to have self-interacting massless spin 2. And in fact, you can go on from here, and I'll leave this as an exercise for you, that you can now imagine, can we do this when we have multiple species? Can I do this if I have like A1, A2, A3, and multiple species of self-interacting spin 2? So I would have this 1, 2 cubed over 1, 3, 2, 3 squared with maybe some G, A1, A2, A3. And what you can do is show that these G's have to satisfy similar kind of identity to that Jacobi, but with some kind of signs messed around. And you can show, it's a nice exercise to try and show that there's no solution for those G's other than the ones indeed where they just decouple into sectors that don't talk to each other. Okay, so in other words, like G's are just decoupled into a bunch of totally non-interacting things. So from there, we also learned it is impossible to have a consistent theory of multiple interacting massless spin 2 particles. If you're going to have a massless spin 2 particle, it's they basically decouple into different universes. Okay, they can't couple to each other in particular. All right, so I hope you're starting to be more impressed. And let me just give you, oh, sorry. And I forgot to say before too, that that we also wrote down the answer for Yang-Mills, right? Because we saw for these A, B, and C, okay? So let me summarize what we've seen so far. So we've discovered that for spin 1, there is a consistent amplitude, but only when the F's satisfy Jacobi. And then we also wrote down the answer. The amplitude is equal to FF over ST plus a different FF over TU plus a different FF over US times the 1, 3 squared to 4 squared. And for spin equals 2, we discovered that the amplitude is 1, 3 to the 4th, 2, 4 to the 4th, and even had to have a minus sign out in front, 1 over STU, okay, with an over some m Planck squared. By the way, I'll leave it for you to puzzle out. This minus sign that we had to have because we had to flip the 1 over u squared, that's that gravity is attractive. Okay, that's the opposite sign that it has relative to over here. That's the fact that the gravity is attractive. But I want you to notice something amazing about these formulas. It's sort of most amazing in the gravity case. In the gravity case, the answer does not look like the sum over 3 channels. It's not something over S plus something over T plus something over U. It's the whole product. 1 over STU comes together, right? That's just a fact about what the actual amplitude looks like. The actual amplitude, there's no way of expressing this formula as something over S plus something over T plus something over U. So, what's going on then? When we compute these things from Feynman diagrams, clearly we get something like something in one channel plus something in the other channel plus something in the other channel, and even some contact terms. Okay, so when we compute with Feynman diagrams, we get something like this. So this sure looks like it's 4 polarization vectors over S plus 4 polarization vectors over T plus 4 polarization vectors over U, and maybe some contact pieces. Okay. So we are learning something. Each one of these pieces cannot be Lorentz invariant by itself. Okay. And in fact, in the conventional language, each one of these pieces is not gauge invariant by itself. So when you break things up in this way, there's no way to interpret the pieces as something Lorentz invariant. We've written them in terms of these Fayko polarization vectors that are not really transforming like 4 vectors, right? Remember, in order for it to really transform like a 4 vector, it had better be that if you replace epsilon goes to epsilon plus alpha p, that the answer stays the same. If I took just this term, it couldn't. If I took just this term, it couldn't. Only the sum of all of them does. Okay, so that's a way of seeing why ahead of time any way of describing this physics in a way that breaks it up as if it comes over the sum of channels has to have something funny associated with it, because the numerators cannot be Lorentz invariant by themselves. And we see why. We see why because the actual amplitude has this product structure, not a sum structure. And the same thing is there in Yang-Mills. It's not quite as dramatic because you don't see all the 3 poles, but it's the product of ST, the product of TU, and the product of US, rather than something which is a sum over the channels at the same time. And so this was all foreshadowed in the very beginning of our discussion from what we remarked on, this difference between the boring and the exciting theories. Okay, so all of this happened because right at the beginning, we had this distinction. These are the theories that have simple Lagrangians with no need for any gauge redundancy or anything like that. And we see that the 3 particle amplitudes don't have any poles. But these theories, the 3 particle amplitudes have poles. And that means that by the time we get to the 4 particle amplitudes, there's no way of expressing them in a way that looks like some of a simple poles. They have to have these interesting product structures. And that means that any way of computing them using polarization vectors has to have some kind of redundancy or some problem in it, because the actual amplitude does not look like this. Okay, so I hope you have a deeper feeling for why physics is forced to be described in this way.
There's a question
Yes.
by Gautam.
Yes.
Yeah, so I was wondering if we could sort of use the same argument for spin equal to 3, because
Yes,
then you'll get a
yes,
YouTube.
let's just do that right now. Let's just do that right now. So if we do spin equals 3, now we're just dead, because the residue in the S channel is equal to something cubed now 1 over U cubed. Now we're just dead. Now there's nothing we can do. Okay, we can't write this as 1 over U squared T, TU squared. Whatever you do, it has to have at least a double pole. So we learn no self-interacting massless spin greater than or equal to 3. Done.
Okay, so but then what happens when you do S equals 3 by 2?
When you do S equals 3 half, it works. Okay, and
Okay.
so and in fact, so let me maybe I can just say I know I've basically run out of time. Can I have maybe just another 10 minutes or so I can finish this thread of
Yeah, of course. No,
okay, great, very good. All right, so as I said, you can look at a discussion along these lines is in section 4 of my paper with the Huang squared. Okay, so if you look at this 2017 paper, I think section 4, we discussed many of these things. And there's earlier nice paper by Megady and Rodina, which discusses many examples like this. But I think now you've gotten the hang of it, you should just do it yourself. I mean, it's a lot of fun, and you'll learn something. But I want to just give you, without going through all the details, just give you a sense for where the constraints come from. It's all the same thing. It's all checking that you look at the residue in one channel, forces poles another channel, and you have to look at their consistency. So if we look, for example, at the interaction between other spins, let's say spin 0, a half, 1, a general spin here. Imagine we have a general spin, S here, but interacting with spin 1, and we have, we have some plus, minus, and let's say plus here. Then there's going to be, this has some index A, this has some index I and J. So this is like some matter. Okay, so I'm just going to call this TAIJ. I don't know anything yet about it being a generator or anything like that. But when I look at the residue here, when I look at the residue of this kind of thing for this sort of amplitude, I, A, B, J, when I look at the residue in the S channel, then I find that it's given by 1 over U, 2, 1, 1, 3 to the 2 minus 2, this spin, the spin of the guy on the outside, okay? Times 1, 3, 2, 4 to the 2s, times some TA, TB, IJ. Okay, so that's just what you get when you, and sorry, this one, I could write here this a little more symmetrically. This is 2 P1 minus P4, 3. But it's raised to this funny power, 2 minus 2s, okay? Okay, and so evidently you see that this is easy to see, right? Because this is a TA here and a TB here. So this is like TAIK, if this guy's K, TB, KJ. So that's how you see that you get the structure TA, TB, IJ. But you get this interesting factor just from gluing together the 3-point amplitudes. Okay, so from here already you see something interesting. If the spin is greater than, if the spin here is greater than 3/2, then 2 minus 2s is negative, and we're dead because this expression has a pole. It has a pole in this crazy quantity that's not ST or U, okay? So we're just completely dead. So that already tells you you cannot have, that already tells you that you cannot have, and this is for S, greater than or equal to 3/2, okay? That you cannot have charged particles, massless charged particles of spin 3/2 or higher. It's just impossible, okay? So for lower spins, so for spin 1 and lower, you can in principle have them, okay? But something has to happen with this TA-TB business. And now if you work out the consistency of the rest of the residues, then you find you have to have that TA-TB is equal to FABC-TC, okay? And the reason is that you get poles in S and U from this Compton amplitude, but those residues have a pole in T, so that can only work if you use this interaction, that 3-point interaction that we already talked about before, which had to be FABC. Okay. So you learn that if the commutator is non-zero, it has to actually equal FABC TC, right? So we see just from these conditions that the only particles that can interact with massless spin 1, can interact with itself with strength FABC, and also with spin equals 0.5 with some TAIJ, which satisfies that TATB is FABC TC. So the entire structure of the Yang-Mills theories is forced. And I can't have no spin greater than or equal to 3/2 that are charged. All right. And if you continue to do this argument now the same way to spin 2, then you discover exactly the same argument. You discover one, this guy here is, these guys are spin S, and this is spin equals 2. Then you discover that one, the analog before, that we couldn't have it for spin greater than or equal to 3/2. Here it just goes up 1 power. This is impossible for spin greater than or equal to 5/2. Okay, basically the power upstairs, in that residue calculation, the power upstairs end up being 2 P1 minus P4 3 to the power of 4 minus 2s. Okay. So if s is greater than or equal to 5/2, this thing would have a pole, and this is dead, right? So we learned something amazing, that if there's a graviton at all, and if we're going to interact with it, it's impossible to have massless particles of spin greater than 2. And we already discovered that if we do have multiple massless particles of spin 2, they have to be in decoupled universes. Okay, so essentially it tells us we cannot have massless particles with spin higher than 2, and the massless spin 2 one has got to be unique, first of all. And the second thing we learn is that the strength of all the other couplings for any spin here, all of these have to have the identical strength. All these have to have the strength 1/m Planck, all equal. And this is the equivalence principle, but anyway, everything else but much more than the equivalence principle, of course. Okay, just nails all of these things, right? But this includes the spin 3/2 is okay. Massless spin 3/2 is okay. All right, so massless spin 3/2 is not ruled out. Massless spin 5/2 is ruled out by these arguments and above. So now we are almost done with our exercise. This is the list of spins we're allowed to have, okay? And it's worth doing a little bit more investigation on this guy, right? So here's the final residue argument is it's perfectly okay to have one massless spin 3/2 and one graviton massless spin 2. This is okay. But can I take the system and just add, let's say I want to add one scalar to it, one scalar phi, okay? So let's now look at the amplitude for the scattering of the spin 3/2 guy. So here's the spin 3/2 guy. 3/2, 3/2, scattering against phi. All right, and of course, there's going to be some residue here in the T channel coming from the graviton. Well, what do you think happens? Surprise, surprise, the residue in the T channel has a pole in the S channel. We've seen that all over the place in these arguments. That means, therefore, that we have to have a particle in the S channel. But what is that particle? What could it be? If this is spin 3/2, what could propagate here to give me a residue in the S channel, well, whatever it is has to be a fermion. And we begin to see that this is only consistent if there are superpartners. Okay, so this, I can't just take a theory of the massless spins we have with gravity and randomly add a scalar. I have to add the scalar together with a fermionic friend, such that the coupling constants here are also one of Ramp-Planck. So the coupling constants have to be related to each other. Okay, and you can really continue along this argument and show that massless spin 3/2 with just one of them, one massless spin 3/2 forces n equals 1 SUSY. And you can really continue with this argument to show that you can have up to n equals 8 massless spin 3/2, but not 9. All right, and that really completes the list. So we can have particles of spin 0, 1/2, 1, 3/2, and 2. And already we saw this one is unique. We can have at most 8 of these, n less than or equal to 8 of these, and that has to go along with SUSY and actually supergravity. Now we can have as many of these as we want. See, we get less constrained as we go to smaller spin. As many of these as we want, but it's associated with the Yang-Mills structure, and these are the more boring guys, okay? They can interact with each other however they want, but the interactions they have with the other guys are totally nailed. Okay, well, anyway, as I said in the beginning of this lecture, this is really what I wanted to cover in the first sort of lecture and a half of these lectures, and it took me 4 lectures to do it. But I hope what you've gotten out of this is a deeper appreciation for how absolutely directly the world we see when we look out the window, its broad properties are totally like nailed by these broad principles of quantum mechanics and relativity. It's really extraordinary. Again, we didn't have to be Einstein to come up with this. Literally, you didn't have to be an Einstein. You have to know quantum mechanics and, you know, smaller Einstein, special relativity, but you don't need all of the fancy stuff, curved space-time, falling elevators, all those thought experiments. That's beautiful. It's the way Einstein did it, but it's somehow even more striking that it's just, there's no other way it could be. You know, it's not like the universe could have been some ugly way and it could have been some pretty way and it decided to be this pretty geometric way. No, it just couldn't be any other way. I think, a totally extraordinary fact. And it also shows, however, this huge difference between, and all of this stuff, where did all of this come from? All of this came from this dramatic shift in the number of degrees of freedom between massive and massless particles. This entire story, right from the beginning, came from that sort of innocuous seeming, but rather dramatic thing. This business about not being able to be a little massless, a little massive being like a little pregnant. Okay, so you can't do that. There's something dramatically different between massless and massive, and it goes right to the heart of all these things that we understand as so incredibly constrained from our even conventional points of view. And the reason I wanted to do all of this, even though it took me twice as long to do, 2.5 times as long to do as I wanted to, is that highlights even more how damn weird it is that we got this guy. Okay. This is the one thing whose degrees of freedom does not jump as we go from massless to massive. And that is the heart of what makes the Higgs so incredibly strange to begin with. That's the heart of the hierarchy problem, which is not an aesthetic problem, is not a problem of people think something is pretty or not pretty. It's a very sort of hardcore problem. But even without talking about it in detail, it should be clear that there is something weird about this guy. And there's a reason why we've seen these other things before. We've seen many of these. Okay, this one, there could only be one of them to begin with. This one, we haven't seen any yet. but there's a reason why we haven't seen 10,000 of these floating around, of these guys, okay? There is something unusual about them, and that's the, without really saying much else, that the 0th order justification for putting the damn thing under a microscope and studying it as experimentally studying it as intensively as we can. But anyway, those of you who are interested in hearing more about the kind of second half of these lectures, and if those of you who want to participate also, I'll prepare some lectures, but we can also really make it a long question and answer session as well. So we could just chat about it. That might be also a fun way to do these things. But anyway, I hope to talk about that as well as in a little bit more detail how we can further this program at possible future colliders, and even what we can do today in order to try to make these colliders have more of a chance of actually becoming a reality. All right, and so I guess with that, I will stop. Thank you very much, everyone.
Right. So let's start now the Q&A. Sounds good.